We are discussing the variational method, and we have presented an introduction to it. We have said that what we do is we write a functional epsilon 0 which has more or less the same form of as the ground state energy. The only difference is that the ground expression for ground state energy would involve the actual wave functions that we do not know, and for epsilon 0 we have some trial guess wave function that we have given. And then we said that this wave function would have some associated parameters which are called variational parameters. What we do is we vary these parameters, change the values of these parameters, calculate epsilon 0, and upper limit theorem tells us that whatever minimum value we get for epsilon 0 is the maximum possible value for E0 or the upper bound or upper limit of E0. So, let us demonstrate this by going back to our old friend the hydrogen atom, right. Of course, we do not have to do this variation treatment for hydrogen atom because we already know the solutions. But since we know the solutions, this hydrogen atom provides a very good test system because we know the expression for energy. We know that this Hamiltonian is like this, okay, and it is ground state, right. So, since it is ground state, I am only bothered with the R part of the Hamiltonian. I do not bother about the theta and phi Hamiltonian because I know that in the ground state wave function there is no theta phi dependence. Also I know the ground state energy. This is something that, well, I am not sure if I have written exactly it in this form earlier, but it is the same as what we have written earlier, okay. I know the energy. Now the good thing is I should be able to use variation method and get something that is close, okay. We have not really derived the theorem yet, we will do that. But right now we are taking it axiomatically for the next 15 minutes or so, and we are working it out. And when I say we are working it out, I am lying because I will not work out anything. I hope you remember our rule. You have to sit in front of the computer with a pen and paper. You are going to work out, okay. I am not going to do so much of integration and all because then it will take a lot of time and it is quite mundane, you can do it. So, we will try to see whether we get a similar expression first of all, and we will try to see whether the minimum value of epsilon 0 that I get is more than E0, okay. If it is so, how much more? Let us proceed. So, let us say I take a trial or guess wave function phi equal to e to the power minus alpha r square. So, alpha is the variational parameter, okay. I am not using this q as variational parameter just as yet. Let us see what happens if I just vary alpha. If it is not good, then of course I want to try with 3, 4 and so on and so forth in the exponent, but we will see what happens. And why am I choosing this e to the power minus alpha r square all of a sudden? Two reasons. First of all, this is a well behaved wave function, is not it, because it goes to 0 at r equal to infinity. It is a Gaussian function. Secondly, I am cheating a little bit because I already know the solution. I know what the 1s wave function is, right, that is e to the power minus kr sort of, okay. It is an exponential decay. So, Gaussian decay and exponential decay, how different are they, okay. What I am saying is an exponential decay is something like this. I goofed, sorry. Not bad. This is let us say an exponential decay, something like e to the power minus kr. And what is a Gaussian decay? Something like this. So, I might as well play around with this parameter alpha and try to see whether I can bring this Gaussian down here, okay, as close to this exponential decay as possible. There will always be some mismatch in near r equal to 0, okay, and I will normalize and get it as close as possible. It will never be exactly the same, but it is not very different. I mean, if we close one eye and shut the other a little bit, we can live with this, okay, and we will see whether we can really live with this or not. Okay. So, phi equal to e to the power minus alpha r square. So, alpha here is the variational parameter that we have discussed already. Great. So, now this is the expression for epsilon 0, okay, we know this. So, what I will do is I will just write down but not solve, I will only give you the final solution, you solve if you want, I mean you should solve and convince yourself that this is correct. This treatment is from Macquarie's quantum chemistry book, not Macquarie and Simon physical chemistry, Macquarie, only Macquarie quantum chemistry. So, I just plug in the expression for Hamiltonian and I write the value, I write the expression for the trial wave function, and all I have to do is just see what I get, and this is what I get. I am giving you the answer. Please work it out yourself, you will have to use a standard integral as usual. Okay, this is what I get. What is the denominator? Denominator is simpler, right, e to the power minus alpha r square. So, multiplied by e to the power minus alpha r square, what is it, and then integrate from 0 to infinity, this is what you get. So, when you divide the numerator by the denominator, you get the value, the expression for epsilon 0 function of phi as 3 h cross square alpha by 2 mu minus e square alpha to the power half divided by root over 2 epsilon 0 pi to the power 3 by 2. Fantastic. What is the next step? What am I looking for? I am looking for what is the value of minimum value of epsilon 0. Okay. How do I change the value of epsilon 0? The only thing that I can play around with here is alpha, variation parameter. So, I keep on changing the value of alpha, okay, and I have to look for the minimum. So, essentially I have to again, well, even though we have said it earlier, I will draw that curve once again. Let us say this is the value of epsilon 0 with respect to alpha, and to keep things simple I will just show one minimum. Let us say this here is the plot. I seek to find the value of epsilon 0 at this value of alpha. So, to do that I have to first find this value of alpha where epsilon 0 is minimum. Now, let us think of what we have learnt in high school calculus. I have a plot. How do I find the minimum of a plot or the maximum of a plot for that matter? Differentiate and equate it to 0, right. For maximum as well as minimum, the slope here is something like this, the slope here is 0, is not it? So, what we have to do is we have to, now what happened? We have to find the minimum value of epsilon 0. To do that, we simply differentiate epsilon 0 with respect to alpha and equate it to 0, right. First derivative has to be 0, that is all. How do you differentiate between a minimum and a maximum, by the way? Yeah, for minimum as well as maximum, this is the first derivative is equal to 0. What about the second derivative? Second derivative, is it 0 or positive or negative for maximum and minimum? I leave it to you to refresh your memory on that. Here, at least in the curve that I have shown, I do not have to worry because I have not even shown a maximum, only a minimum point is there. Okay. So, differentiate this and equate it to 0. What will you get? You will get a value of alpha, is not it? That value of alpha turns out to be mu square e to the power 4 by 18 pi cube epsilon 0 square h cross to the power 4. Okay. I have given you the answer. You should not be satisfied with that. You should differentiate it, equate to 0, see what value of alpha you get, and convince that whatever we get, convince yourself that what we have written here is indeed correct. Please do it. Okay. So, we plug in this value of alpha here in the second term and in the first term. What will happen? I will get some expression for epsilon 0, it is a function of phi, and that expression turns out to be minus 4 by 3 pi mu e to the power 4 by 16 pi square epsilon 0 square h cross square, and I am calling this E min. Perhaps I should have called it epsilon min, but then I am using a different convention than Macquarie. I wanted to get back and be at par with him. So, I have written E min, which is what is written in Macquarie's book. E min turns out to be minus 4 by 3 pi e to the power 4 by 16 pi square epsilon 0 square h cross square. That turns out to be equal to minus 0.424 mu e to the power 4 16 pi square epsilon 0 square h cross square. Yeah, I just clean it up a little bit for you. So, this is what we have get minus 0.424 multiplied by this factor, and this is what we have got from the exact solution, minus 0.500 multiplied by the same factor. So, is that good or is that good? It is good. First thing we see is that this is a demonstration of the upper limit theorem. E min is greater than E0. It is close. Since it is close, I say the agreement is good, but it is still greater than E0, it is not less than E0. That is point number 1. This is not a proof, by the way, it is an illustration. Now we can think that okay, we have got 0.424 and here it is 0.500. How can I get closer to 0.500? And the answer would be by introducing some other parameter. I have taken a Gaussian parameter. So, instead of 2 I can write q and I can play around with q, and you know what will happen if q goes closer to 1, and I am saying this because I know what 1s wave function is. If q goes closer to 1, then the match should be better. So, the energy that I get should be closer to the energy that I get from the exact solution. Besides, I could multiply this by a number maybe so that you get the correct function, but that may not make any difference. So, I can play around with the exponent here. So, if you put in more parameters, I get a closer match. Well, when you do this kind of what I should say curve fitting, if you use more parameters, you always get a better match, and sometimes there is this danger which is called over parametrization. Here we do not have to worry about over parametrization, that is great, because remember that cartoon on the cover page of the previous module. We cannot do better than the best. Whatever we get is always more than the actual value of energy. So, even if you over parameterize, it is not a problem. It is a beautiful consequence of the upper limit theorem. Okay? So, I can actually increase the number of parameters, I can have trivial parameters eventually, but does not matter. So, if you have the time and if you have the capability, you can just keep on increasing the number of parameters. So, what we have to do is we have to optimize this epsilon 0 functional that is related to energy with respect to each and every parameter. So, you need to do iterations, and you can understand that here we are looking at a very simple system, we are working with only one parameter. For larger systems there will be many parameters. So, if I try to do it by hand, it will take me so much of time that by the time I am done the problem may not be relevant anymore. So, you have to use computers. So, requirement of this excessive large number of calculation requires an interfacing of chemistry with computers. Okay. Conventionally, when you think chemistry, when you talk about chemistry, you think of color, smell, many times bad smell, beaker, conical flask, weighing balance, yeah. But now we see that computers seem to have an important role to play in chemistry, because you cannot do these computers any longer without you cannot do these calculations any longer without using good computers. So, this iterative method is sort of our introduction to the requirement of computational chemistry. Of course, we are nowhere close to the actual thing yet, I mean in this course, right. Computational chemistry nowadays has developed into a huge field. We will not get into computational chemistry, but we are taking baby steps towards it. So, what I am saying is that this is the first baby step. Our introduction to iterative method is a first baby step towards this vast field of computational quantum chemistry. And in doing so, one thing that might happen is that we might lose sight of exact solutions. Is that good or is that bad? See, here we use some arbitrary function, no? E to the power minus alpha r square Gaussian function, not really the exact solution, yeah, but still we got it. And then we said that we will introduce more parameters. So, we will deviate further and further and further from the exact solution. Is that good or is that bad? But it is good in the sense that sometimes we may not even know the exact solution. That is the reason why we want to do variational method rather than perturbation theory, right. So, if you can forget about the exact function, that is great, yeah, just change the number of parameters, do not bother about the wave function, bother about the energy, that is the good part of it. The bad part of it is that we might lose a little bit of physical insight. So, you see all these orbitals that we talked about, after some time these orbitals may not be necessary anymore. We can just construct the wave function. Here I have used one Gaussian function. I can take a linear combination of many Gaussian functions, right. I can take exponential functions, I can introduce some asymmetry factor. So, this way I can actually synthesize the wave function by using mathematical functions, simpler mathematical functions, which is great because I can with enough computational power I can find the energy. And from the point of view of a conventional physical chemist, you might be a little sad because you will not be able to perhaps after a while say much that is in relation to your good old 1s2 s2p orbitals, or maybe you can, we will see. Okay. Now that we have illustrated that this upper limit theorem works for hydrogen atom, let us move forward to a formal proof of the theorem. And let us say once again that we can write this kind of Schrodinger equation for this arbitrary system, and let us say psi i's are constitute the complete orthonormal set of unknown wave functions. Let us say there are n such wave functions. Okay. Here again I deviate a little bit from Macquarie's treatment. Macquarie has written n, I am writing I, okay, because I thought that you use n for a particular value and then use n as an index, you might get confused. So, I am using I, which is an index. Alright. So, now let us define an arbitrary wave function that we will work with. Remember phi, we defined phi, and this time I say that I can write phi as a sum of Ci psi I. Is this valid? Actually it is, because see what are psi i's? We are taking an orthonormal set, right, a complete orthonormal set. So, they are like the coordinates of the function space. I take some arbitrary function in that function space, I want to work in that function space because the system is same. I should be able to express it in terms of the coordinates of that space, the modes of that space, right. That is why it is perfectly valid to write phi equal to sum over I Ci psi I. Okay. I construct the arbitrary wave functions that way, and as we have discussed earlier, we define epsilon 0 to be integral phi star h phi divided by integral phi star phi over the entire function space. Okay. So far so good. I hope we can proceed. Yeah, let us go proceed. So what I will do now is I am going to write it out, and I have written it out completely. I should have animated a little bit more, please do not get scared, I will go term by term. Well, I should have ideally written a summation, but I myself get confused sometimes if there are too many summation signs. So, I have actually opened the summation. So, this is what will happen, phi is what? Phi is this summation, right. So, I have just opened it up, C1 psi 1 plus C2 psi 2 plus C3 psi 3, so on and so forth until Cn psi n. Okay. So, the general term here Ci psi I sum over I, right. So, actually I am working with its complex conjugate. Remember, a wave function or function in the bra vector is actually its complex conjugate. This left multiplies h operating on phi, which is h operating on C1 psi 1 plus C2 psi 2, same thing. In the denominator we have integral C1 psi 1 plus C2 psi 2 etc. complex conjugate multiplied by C1 psi 1 plus C2 psi 2 etc. Okay, integrated over all space. Now, what will I do now? I will remember that H psi I is equal to Ei psi I. Okay. So, what happens when H operates on this? Let me write. So, what this means essentially is, say H psi 1 is equal to E1 psi 1, why have I put the arrow there, this. So, what is H operating on C1 psi 1? That will be equal to C1 into E1 psi 1. Remember, we are working with linear operators, but I have written it so horribly, I think I will erase it and I will write the whole thing once again. What I am saying is this Schrodinger equation is something like this. H operates on psi 1 to give me E1 psi 1. So, what happens when H operates on C1 psi 1? That is the same as C1 multiplied by H psi 1, is not it? Linear operator. So, this will be simply C1 E1 psi 1. Similarly, H operating on C2 psi 2 will be C2 E2 psi 2, so on and so forth. Okay. So, essentially this ket vector will become sum over I Ci Ei psi I. Perhaps you understand, perhaps I do not need to explain in such meticulous detail, but I still will in case somebody does. So, this is what it is. I have not worked with the denominator yet, I hope I have not made any mistake anywhere, yeah. So, this is what I get. In the bra vector I have C1 psi 1 plus C2 psi 2 etc. sum over I Ci psi I this. In the ket vector I now have sum over I Ci Ei psi I. Okay. Now, let us remember that these psi's are all orthonormal. So, what happens when I try to simplify this numerator or denominator a little further? First, let me take this term Ci psi I and this. So, I may well write this Ci psi I and Ci E1 psi I. So, this will give me integral Ci in ket vector, sorry C1 in ket vector, C1 psi 1 in bra vector. Yeah, is there anything else? Well, let us not forget that I have psi 1 here as well. Okay. I can take these coefficients out of the integral, they are constant. So, that becomes C1 star C1, right. This is actually C1 in bra vector, remember it is actually C1 star. So, C1 star C1 comes out and inside the integral you are left with integral psi 1 star psi 1 d tau. What is that? That is equal to 1 because they are normalized. Similarly, if I take this term and this term, what will I get? I will get C1 star C2 integral psi 1 star psi 2 d tau, but then orthonormal, right, orthonormal, right. So, these are all orthogonal to each other. So, this integral must be equal to 0. So, I am only left with C1 star multiplied by integral psi 1 star psi 1 d tau. Similarly, I will get C1 star C1 multiplied by integral psi 1 star psi 1 d tau. Similarly, I will get C2 star C2 integral psi 2 star psi 2 d tau. So, the general term here will be Ci star Ci integral psi I star psi I d tau. So, ij kind of term will not be there and it will be a summation over I. What will the denominator be? Similarly, denominator also has to become sum over I Ci star Ci, right, because take these two terms again, maybe I will take these two C2 psi 2 and C2 psi 2 here, that gives you C2 star C2 integral psi 2 star psi 2 all space, and if I take say C3 psi 3 and well Cn psi n, then I get C3 star Cn integral psi 3 star psi n over all function space, which is equal to 0. Right. So, this is what I get. Did I goof up a little bit in the numerator? Actually I did. See here what I have written is I have forgotten something. I have forgotten that I have E1 also EI. So, numerator turns out to be C1 star C1 E1, right, because the integral of psi I star psi I over all function space is 0 plus C2 star C2 E2 so on and so forth. Denominator is C1 star C1 plus C2 star C2 plus C3 star C3 so on and so forth. Okay. So, I will write it as summations that I have written here and I made a mistake while writing the numerator. So, this is sum over I Ci star Ci Ei divided by sum over I Ci star Ci. Okay. Now, what do I actually want? I am trying to prove the variation theorem, upper limit theorem. So, what I want to know is whether this epsilon 0 minus E0 is greater than equal to 0 or not. So, let me subtract E0 from left hand side, then I have to subtract it from right hand side also. So, this is what I get, yeah, and these steps are simple. So, I will just rush through. So, this is basically one summation minus another summation, alright. So, I can just make it one summation and in both the cases coefficient of Ei is Ci star Ci. So, I can write like this, Ei and E0 both coefficient is Ci star Ci. So, I get this, numerator is sum over Ci star Ci multiplied by Ei minus E0 divided by Ci star Ci. Now, please remember what is E0. E0 is our definition of ground state energy. What is Ei? Ei is the energy of some excited state, okay, some excited state for I is not equal to 0. So, will you agree with me that Ei minus E0 has to be positive or at most 0 when I equal to 0, yeah, because energy of the ground state is the lowest, right. For all values of I other than 0, energies are higher and higher, that is why it is called ground state. Your ground state cannot be above the excited state. Well, in case of some human beings it is, but they are not quantum mechanical systems, fine. So, Ei minus E0 has to be greater than equal to 0 because E0 is the lowest value of energy among all the Eis that are possible. Remember, I is the general index, okay. In fact, I should have perhaps written 0 here also. If I define I to be 1, 2, 3 so on and so forth, I am not writing 0, well whatever, well the 0 means ground state. That is point number 1. Point number 2 is what is Ci star Ci? Some complex number multiplied by its complex conjugate yields a real number. Can it ever be negative? Never. Complex conjugates are defined in such a way that when they multiply each other you are going to get a positive real number, is not it? Yeah. If there is any confusion, please go back to some basic book of complex numbers, 11-12 level book, your doubt will be cleared. Otherwise, just believe me when I say that Ci star Ci has to be a positive real number. So, this is also 0. So, in the denominator I have something that is positive. In the numerator Ei minus E0 is positive and I just said that Ci star Ci is also positive. So, this epsilon 0 minus E0 is a positive quantity divided by a positive quantity which is a positive quantity. Hence, we have been able to prove the variation theorem or upper limit theorem which says that epsilon 0 minus E0 is greater than or equal to 0, or in other words the functional epsilon that we calculate by varying the parameters of phi can never be less than the actual energy, and that is a saving grace. Okay? That is why variation theorem is so useful. So, that is what we have learned today. We have done it from quantum chemistry's book by Donald McQuarrie. We are going to use Pillar's book also in this context. What we will do next is that now that we have proved this theorem, we are going to see how we can get an expression for ground state of harmonic oscillator, how we can get an expression for the energy levels of particle in a box using variation method, and somewhere in the line, maybe before this or after this, we will show that for trial functions that depend linearly on variational parameter, we get a secular determinant, and the moment we get a secular determinant the solution becomes very simple, right, and that becomes a cornerstone in trying to solve variational problems. And then finally we are going to use the variation method and also perturbation method in multi-electron atom, right. So, all this is coming up in the next few modules. As they say in FM channels, stay tuned.